The lambda operator allows us to define functions on the fly. This expression is equivalent to the add1 function that we defined in the last video. Let's take it apart and look at the pieces. We generally need these parentheses. Without them, the lambda expression would extend all the way to the end of the line, which we usually don't want. This is actually a backslash, but we pretend it's a lambda. As the book points out, it kind of looks like the Greek letter lambda if you squint hard enough. Why lambda? This is a reference to the lambda calculus, a logical system invented by Alonzo Church in the 1930s. You'll eventually encounter it again if you study the theory of programming languages. Here's the argument to our function, and here's the result. So, lambda allows us to create a function without giving it a name. This is useful for the same reason that anonymous inner classes are useful in Java. Sometimes we need to define something that we're only going to use in one place. Since good names are hard to come by, we don't want to waste them on such ephemeral entities. We'll see more examples in a moment. First, though, take a look at these two functions. The first one adds up all the elements of a list. The second one multiplies the elements. In fact, these are equivalent to the built-in functions sum and product. These two functions are extremely similar. Aside from the names, the only differences are the result used for the empty list and the function used to combine elements. This sort of redundancy should bother you. Repetitive code is difficult to write, read, and maintain. Object-oriented programming addresses this problem with inheritance. Functional programming's answer is higher-order functions. The fold_L function captures this common pattern of combining successive elements of a list. Fold_L plus 0,536 is equivalent to 0 plus 5 plus 3 plus 6. That is, it uses plus to combine the initial element 0 with the first element of the list, 5. It then uses plus to combine that result with the next element of the list, 3. Finally, it uses plus again to combine that result with the last element, 6. It uses plus to fold up the list into a single value. Can you figure out how to use fold_L to multiply the elements of a list? That's right. Thanks to partial application, we can even use fold_L to define add_all and multall more concisely. Here we're saying that add_all is just the function that we get when we supply fold_L with the first two of the three arguments it needs, the combining function and the starting value. Fold_L folds up a list from the left. Fold_R folds up a list from the right. This would make a difference for a function like subtraction. Fold_L minus 0, 1, 2, 3 is equivalent to 0 minus 1 minus 2 minus 3, while fold_R minus 0, 1, 2, 3 is equivalent to 1 minus 2 minus 3 minus 0. With fold_L, the first thing we do is 0 minus 1. With fold_R, it's 3 minus 0. We can use folds to write all sorts of useful functions. First that returns the first element of a list that satisfies some function, or a default value if none of them do. The definition is a one-liner. This pulls together a number of the concepts we've discussed. Like fold R, first that appears to take three arguments: a function, a default element, and a list. It returns an element. Of course, it's actually curried and can be partially applied. The second and third arguments are the same ones that will be passed to fold R, so we just leave them out of the definition. First that works by going through the list from right to left. At each point it has x, the new item, and acc, the result accumulated so far. If f of x is true, that's the result. Since we're folding from the right, the last satisfying item encountered, and hence the result, is the first one in the list. Last that is defined almost identically. The only differences are that we fold from the left instead of the right, and the order of the arguments to the lambda function is reversed. Fold L1 and fold R1 are similar to fold L and fold R, but they don't need a separate starter value. They just start with the first or last element of the list. These are appropriate when what we're trying to do doesn't make sense for an empty list. For example, the function argmax, defined here, gives us the element of a list for which the function f returns the highest value. We can use it, for example, to find the number among those in a list with the largest square. Here it is defined using fold L1. Argmax works through the list from left to right. At each point, it looks at the best element it has accumulated so far, acc, and the new element, x. It returns whichever has the larger value when f is applied to it. I'm going to gloss over the $ and dot operators. They mostly allow us to write expressions in slightly different ways that might not be any easier to read. I'd rather just use parentheses, but then I have a background in Lisp and Scheme, languages that some say consist almost entirely of parentheses. I will mention one trick. Suppose we want 2x plus 1 for each x in a list. We could do this with a lambda. Alternately, we could compose the 1 plus function with the 2 times function using the dot operator. This builds the same function as the lambda expression. It's a little shorter. Is it clearer? Maybe. We can use what we've learned to make our old tic-tac-toe program a bit shorter. Here's what the winner function looked like before. One shudders at the repetition. We can shorten it with first that. Now line is the winning line, if any, or the empty list otherwise. We use first that to find the winning line. It's the first of A, B, C, D, E, F, etc., for which all three elements are the same, but are not dots. The code that finds all of the succeeding boards appears several times. Let's define a function to take care of that. This makes value much clearer. If the game is not over and it's x's turn, the value of the game is the maximum of the values we would get if we considered each place x could move and let O move next in each one. Best of could be defined trivially with argmax. In fact, since best of is only used once, we can do away with it entirely. Best move is the successor that would give us the largest value if O moved next. These examples illustrate a good practice to adopt, no matter what language you're using. When your code becomes redundant, awkward, or just too long, find a way to define something that will let you say what you have to say clearly and concisely. This kind of abstraction is at the heart of computer science.